conference. Top of the word conference in Germany, right?
Okay. With Sean.
All right. So thank everyone for coming to this week's crypto seminar. The talk will be given by Emrah on solving Knapsack problem.
Today I'm going to talk about Knapsack problem, and it's actually applications in cryptography towards the post-quantum secure algorithms. I will first start with defining the Knapsack problem and given the crypto systems based on the Knapsack problem. Then I will go through with algorithms for solving Knapsack problem. One group of algorithms is generic algorithms, and the other use the lattice reduction. And in the end, I will give you our algorithm with Dr. Karagina, actually, as we believe that this is a post-quantum secure algorithm. So let's start with Knapsack problem. If you are given n integers a1 to an, and the positive integer sigma, the Knapsack problem tries to find a solution epsilon 1 to epsilon n such that sigma is a combination of ai's where the coefficients are epsilon I. Of course, this Knapsack problem gives you a solution if there exists such a solution. Okay, this is a decision problem. This problem also known as 1-0 Knapsack problem or subset sum problem in cryptography. Decision problem is NP complete, and finding the solutions for that problem is NP hard. We say the elements AI as the Knapsack elements, the Knapsack size is n, sigma is our target sum, and epsilon 1 to epsilon n is our solution. Here I give it another definition, alpha Knapsack problem. Alpha here determines the weight of the solution, as in here. Epsilon, the weight of epsilon, I mean the summation of AI's, is alpha times n. And for a random Knapsack problem, actually you expect that half of the size, which is n over 2, is 1 and the rest is 0. Okay, that's why we say a random Knapsack problem is actually 1/2 Knapsack problem. Okay, but in crypto systems, actually, we are focused on that alpha because to have a unique decomposition, or avoiding the decryption failure, they pick alpha very small. Okay, not 1/2, but very small, like 0.2 or 3 or 0.1, even 0.1. So the number of ones in your solution are very small with respect to the size of the Knapsack size, with respect to n, which is the Knapsack size. Okay. So crypto systems based on Knapsack problem. The first one is Merkle-Hellman Knapsack crypto system, introduced in '78. This is actually just 1 year before this crypto system ISA was introduced, and we still use ISA, but we don't use Merkle-Hellman crypto system because it was broken in '82 by Shamir. It just lived for 4 years. Then it was totally broken. Here we choose a private key WQR, which is where a W is a super increasing sequence. Do you know what is super increasing sequence? Anyone knows? Super increasing sequence means the J of W, J elements of the sequence is greater than the sum of the sum of other components, other wi's from 1 to j minus 1. Okay? For example, here w is 2, 7, 11, 21. As you see, 11 is greater than sum of 2 and 7, which is 9. 21 is greater than the sum of these three numbers, because the sum of these three numbers is 20. So 21 is bigger than this sum of these three numbers. 42 is bigger than sum of these four numbers, so it goes on like this. Okay? So this is super increasing sequence. Then we choose a random integer q, which is bigger than sum of all omega i's. Here we choose 881. The sum of omega i's here, wi's here, is 776. So we choose a bigger number than 776. And r is a random integer relatively prime to q. Okay, this is our private key, w, q, and r. And we publish our public key as we compute, as we multiply wi's with r in modulo q. Here, 295 is actually 2 times 588 in modulo 881. Okay? Or 310 here is 11 times 588 in modulo q. As you see here, this sequence W is a super increasing sequence, but this public key has no such a property. It seems like a random sequence. Okay? As you see here, it seems a random sequence. So that's why you hide your super increasing property of omega W by multiplying all the elements with some number r to have this public key. So encryption is really easy. You have the public key, so you just add the public key elements where mi is 1. For example, if your message is 0110001, I mean the second and the third and the last element is 1, so you just add the second element in your public key, third element in your public key, and actually the last element in your public key. The rest is just 0. Okay? And we get 1129. So how do we decrypt this ciphertext? Remember, we multiply all the private key elements with r. So we need to divide this ciphertext with r so that this C dash becomes our original knapsack sum. Okay? Before, C equals to mi times public key of I, public key I. But when you multiply this public key I with R inverse, so you remove the multiple R. Continuing our example, we get, for example, for C dash 372, and how can we compose this 372 into our messenger? Remember our private key, which is 2, 7, 11, 21, 42, 89, 180, and 342, 354. So starting with the biggest element, you start to subtract as you can. For example, we can subtract the last element, 354, from 372. We get 18. We cannot subtract the other elements, 180, 180 or 89 or 42 or 21 from 18, because these numbers are bigger than 18, so we cannot subtract, okay? But we can subtract 11, and we can subtract 7 in that. So 354s, 11 and 7 are the elements in our private key corresponding to 8, third and second positions. So our message is we just put ones into the positions, the 8th position, the 3rd position, and the 2nd position, and the rest is 0. Okay? So this is how Merkle-Hellman Knapsack crypto system works. It was broken by Shamir in 82 because he showed that if the elements in your super increasing sequence is multiplied with a number, okay, it can be breakable in a polynomial time. Remember, this was our private key, part of the private key, the super increasing sequence. This seems a random sequence. But even it seems a random sequence, Shamir find a way to convert, to break this crypto system. So the vulnerability of, the problem in this crypto system is using a super increasing sequence. Shortwave crypto system, there's another crypto system proposed in 84. We have two finite elements. This works on the finite fields. We have two finite fields, FQ and FQM, where the property here is you should choose FQ to the M, the extension field, so that the discrete logarithm is easy. Because Shortwave computes discrete logarithms to construct its private key. Public key. Private key, T, G, pi, and D. T is chosen as a element in the extension field. By the way, I will say this is FQ is a base field, FQM is the extension field. So you choose an element above, in the extension field with minimal polynomial of T's of degree n. It is equal to the extension degree, which is n. You choose a primitive element generating FQM star. You choose a permutation 1 to q, and then you choose an integer d as a noise. We will use this d as a noise as a shift on the public key. This is how the public key is computed. This alphas are in your base field. These are FQ in the base field. Okay. With a suitable permutation here, you mix them. Okay. And you move this element to extension field by adding just T. This element was in the base field. By adding T, you move this element, you push this element into extension field. Okay? This element is in the extension field, in the FQM. Then you compute the discrete logarithms of those elements. There are Q alpha i's, and for each alpha, you compute the discrete logarithm of T plus alpha i's, or alpha pi i's. And you just shift that numbers. These numbers are actually is from 0 to qm to qm, q to the m minus 1, corresponding to the size of FQM star, the multiplicative group of the extension field. And you just shift that numbers with D by adding D. Now this is your public key. How do you do the encryption? Very similar to Merkle-Hellman crypto system. You just pick the public key components if this MI is 1. Otherwise, 0 times public key, it doesn't affect the sum. And how do you do the decryption? If you obtain the ciphertext C, you first remove the noise, because in your elements there was plus D noise, right? And you know that, by the way, I forgot to tell that this message is of weight m. I mean, this is not a random message. The number of ones in this message is absolutely m. Okay? I mean, the weight of the message is fixed. By the way, this is not h, this is m. So, since there are m many ones, so there are m times d many noises, so you remove the noises to get the c dash. And you know that c dash actually, okay, c dash, you get the c dash, and you compute the g to the c dash, which gives you an element in the extension field, and you just factorize or decompose this element in terms of factors, in terms of multiplication of elements written as t plus alpha ij's. Here there are, this is also m, there are m factors of this elements. Okay, if you decompose this element s, you will have exactly m many factors. And then after you get the roots, you just do the inverse permutation to determine which bit of m is 1. I will give a small demonstration about this Schwarz crypto system. For example, our parameters are for the Q211 and our extension is 24. So we get our base field and the extension field. Okay, final field of size 211, final field of size 211 to the 24, and these are your elements in your base field. This part generates the private key. This is T in extension field, but written as a vector space over the base field. Okay, this is actually a vector, but you can see this vector as a extension field versus base field. Okay, this is your G is your primitive element, pi is your permutation, and D is your noise. When you compute the public key, this is all your public key. You see? Very large numbers. And the size of this list is Q. There are 211 elements here. So this is your public key. This is the encryption decryption part. If you are given a message here, by the way, be careful. The number of ones here is, there are, 24 ones in this message. Okay? Exactly, the weight of this message is 24. Equals to the extension degree. Okay? Then your ciphertext is a large integer, a big integer. You compute the, after removing the noise, we get C dash, and we compute the element in the extension field, and this is the representation, the vector representation of this element. Then you have this polynomial. Okay, this polynomial is actually the multiplication of t plus alpha i's. There are 24 alpha i's here. So the degree of this polynomial is 24. Okay? And your goal is just to decompose this, finding the factors of this polynomial. And the factors of this polynomial is 0, 4, 9, blah, blah, blah. There are 24 roots. Be careful, these roots are in the base field, not in the extension field. These roots are in the base field. This G and G to the C dash, this element is in the extension field, okay? But the roots of this polynomial is in the base field. Then knowing these roots, you can easily apply your inverse of the permutation. These are like the positions of ones, but applied pi permutation. So you should inverse permutation to find the exact positions of ones. Okay? Then you construct the message.
So remember your last slide, H equals M.
Sorry. Yeah, H is equal to 10. And these are the proposed parameters for Shor-West crypto system. I made two groups because the first group is broken by Shor and Höner in 1995 using a lattice reduction, and the rest broken by Vodanay in 1998 using the algebraic techniques. What you see here, actually, what you see in these numbers. For example, this 2, 4, 3. This is not a prime number. This is like prime power, right? 3 to the 9. I'm sorry, 3 to the 5. Yeah, 3 to the 5. Or 256. This is 2 to the 8. Prime power, not a prime number. Okay, 211 is a prime number, but its extension is 24. It's not a prime. So, if you consider the base field and the extension field, there are many subfields between these two fields because these extension degrees are not prime numbers. Okay? So, exploiting this algebraic vulnerability, Vodanay broke the system, but he proposed to use proposed to choose both Q and M as prime numbers. Okay? To make your algebraic structure strong. To remove all the subfields. Under this proposition, everybody believes that Shor-West system is secure. Okay? Even I say Shor-West is broken, it's because of the parameters, not because of the crypto system. If parameters are chosen carefully, that both of them are chosen to be prime numbers, then there is no problem. Other Knapsack crypto systems, power line system proposed by Lenstra, and fractional power line system proposed by Camino and Chabana. These two power line system is a variant of the Shor-West, and they make a good change on this Shor-West. As you remember, you need to compute the discrete logarithms to compute the public key. Okay, to construct a public key, you should compute the discrete logarithms. They say we don't need to compute the discrete logarithms, just remove this part, okay? And instead of using additive knapsack, let's use multiplicative knapsack. Okay? By additive knapsack as, let's say, epsilon I times AI. Okay, this is your sigma. We can change this problem to multiplicative knapsack as multiplication of choose a generator in your group Okay, so this is your multiplicative knapsack problem. You can compute this part, let's say C dash and C bar, and you can say these are your basis elements, A, I, bar, and you take the power of epsilon I, which means if epsilon I is 1, you just use the base element. Otherwise, you don't use this base element in your factorization, in your decomposition, or in your multiplication. Okay. Other crypto systems, Nasha, and Star crypto system, Okatamo, Tanaka, Ushiyama, OTU. This crypto system is proposed as a quantum public key crypto system based on based on number fields. They use number fields, and they use knapsack problem in number fields. And they say this is a quantum, quantum safe crypto system. And another in 2007, Murakami crypto system using CRT. And there are also many others, but all of them are based on knapsack problem. The security of the security is based on the knapsack problem. So let's go through with algorithms to solve knapsack problem. I will start with the group of algorithms as generic algorithms to solve knapsack problem. You are given a knapsack elements A1 to AN and a target sum sigma, and your goal is to find epsilon 1 to epsilon n as your solution. This is your goal. How do you do this? The basic idea is list all the possible solutions. Okay? This is the basic idea. And name method, just construct a single list and with all possible solutions, construct a list. This is your epsilon candidates and sigma's corresponding this. You start with all zeros, all the possible binary vectors and compute the corresponding sigma, and you know that your exact solution is one of this, right? But the size of this list is 2 to the n. So this idea is not so good. So we go through with smart methods, construct many lists, okay, and reduce the list size, but merge them with smartly and very carefully and quickly to find a solution. Okay, instead of creating a one list, we will construct many lists. Okay, and then we will merge those lists smartly. Memory complexity here is the total size of the list. Time complexity is the time consumption for the merge of the list. For example, Shroper-Shamir algorithm, they divide the knapsack into 4 equal subsets. Then in each list, L1, L2, L3, L4, he computes all the possible solutions as I did here. But be careful, the vector size here is n, right? But when you divide this knapsack set A1 to AN into 4 equal subsets, this length becomes n over 4. So your list was of size 2 to the n, but you decrease your list size to the n over 4. Okay? So you create 4 lists, L1, L2, L3, and L4, each of size 2 to the n over 4. Then you use an algorithm, 4-way merge algorithm, known by computer science people very well, but not in the maths people, to merge them smartly so that your exact solution is one solution from this one solution from this 2, one solution from this 3, and one solution from this 4. By the way, the binary vectors corresponding to the solutions are xk, x1, x2, x3, x4. Okay? So you find 4 candidates for your solution, then you just combine them. You just say, this is my epsilon, this is my exact solution, is a combination of x1, x2, x3, and x4. Time complexity is 2 to the n over 2. By the way, for the time complexity and the memory complexity, I just focus on the coefficient of n, okay? well, I mean, all of the generic algorithms are have the complexity, exponential complexity in terms of 2 to the c times n. So for the time complexity, I just focus on this coefficient Tc. For the memory complexity, I just focus on this coefficient Mc. So for the random knapsack, Tc is 1/2 and Mc is 1/4. This means the memory complexity is 2 to the n over 4 because n times 1/4. Time complexity comes from merge algorithm is 2 to the n over 2. It's related to the size of your list. It's the square of your list size. For random knapsack, I'm sorry, for alpha knapsack, which means if the weight of the solution is not 1/2 of the whole size, I mean, it's not n over 2. It is less than n over 2. So you use the entropy function here, and this entropy function, let me draw this entropy function graph. Do you know the entropy function? It is 1 on 1/2 and zeros at 0 and 1. This is alpha, this is h of alpha. So this is entropy function. And h is given as, I mean, there is a formulation for h, but we don't need to give it. This graph is enough. So if your alpha, the number of ones, the portion of number of ones, is somewhere here, as you see, it decreases down. Okay? I will give you a toy example. For example, if your A is 224, and there are 8 AIs here, and your target sum is 313. So you divide this A into 4 subsets. One subset 22, 25. Another subset 32, 57. Okay, you divide this A into 4 subsets. Then you create a list, 4 lists. You create 4 lists corresponding to this subsets. For example, if you take none of these numbers, then the summation becomes 0. If you take just the first element, then the sum becomes 22. If you take the second element, then the sum is 25. If you take both of the elements, it becomes 47. So, is it to understand this construction of list? By dividing into subsets, you create all possible lists. And you try to find sigma 1, sigma 2, sigma 3, sigma 4. Sigma 1 here, sigma 2 here, sigma 3 here, sigma 4 here. The last components. To be as a decomposition of 313. So 313 can be written as a decomposition of 0, 90, 60, 160, 163. 0 comes from here, 90 comes from here, 60 comes from here, 163 comes from here. And you just take the corresponding coefficients. For 0, 0, 0. For 90, 1, 1. For 60, 1, 0. For 163, 0, 1. And then you just combine them. And this is your solution. Okay? So we achieve our goal. We reduce the list size to 2 to the n over 4. We use a smart algorithm to merge the list, which is 4-way merge algorithm. Okay? And the running complexity of this algorithm is the square of the list size. The list size here are 2 to the n over 4. Square of this list size is 2 to the n over 2. Okay? Both of the complexities are less than 2 to the n, which is corresponding to the naive method. I mean, creating a single list of all possible solutions. Okay, this is the approach proposed by Schroeper and Shamir. Graham and Jew propose another way of construction list. Not all the possible solutions. Okay, not all the possible epsilon i's. Instead of taking all the possible epsilon i's, you just focus on the weight of the solution. Okay? It means that if your knapsack is size 8, okay, then weight is what? Your expected weight is 4. Okay? Then you create 4 lists. Wait, let's say this is your L. You create 4 lists where each solution is of weight L over 4. For the previous example, L over 4 becomes 1. Okay? So what does it give you? If the weight is 1, you have n elements, right? Knapsack elements. You have n knapsack elements. You just choose you just have to choose one element. It may be, by the way, 2 or 3 or 4, I mean, for the other examples, and combine them. It's like, it may not be a good example, but I will change these numbers to 16, and this is 8, and this is 2. Okay? For a knapsack of size 16, my expected weight is 8, and I divide this knapsack solution so that each of the solution is weight 2. So each of weight 2 means you pick all the two combinations of the knapsack elements. A1 plus A2, A1 plus A3, all 2 combinations. A1 plus A4. Here, 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 and here. Okay? This 4 list seems identical. But to reduce the list size, you import another idea here to reduce the list size. You just pick save the sums where, for example, in the first list, if they are equal to R1 modulo n. In the second list, you just save the solutions if they are equal to R2 modulo n. Okay? I'm using a modular reduction for a random numbers R1, R2, R3, and R4 actually. You reduce the list size. Okay? I mean the solutions here, sigma 1 equals to R1 modulo n. Here, this is sigma 2 R2 modulo n. Okay? And goes on like this. So it reduces your list size, and you use again the 4-way merge algorithm to merge them. And these are the given complexities. For random knapsack, it was 0.5 in Shamir algorithm. It reduced to 0.337. This was 0.25. It just increased. I mean, a little increase in the memory complexity, but time complexity goes down. Okay. Baker, Coran, and Joe, instead of using zeros and ones in your solution, you extend your representation to -1, 0, and 1. Here, in construction of those lists, you were just using zeros and ones. Okay? For example, A1 plus A3. As the coefficients are 1, 0 times A2, 1 times A3, blah, blah, blah. These coefficients were just 0 and 1. In new proposal, they start to use also -1. So you can also import, for example, -1 times A1, 0 times A2, 1 times A3. Okay? You can also include this summation in your list. But in the end, you should remove these negative ones because your exact solution doesn't have a coefficient -1. It just has a 0 and 1s. It's a binary vector. So it doesn't have a -1. But in the construction list, you can have -1 if you can remove all the negative ones in the end. And this is the complexity, the time complexity, memory complexity is reduced to 0.291. And this is the graph for the alpha knapsacks. As you see here, for example, if alpha is 0.1, which means the number of ones in your solution is 1/10 of all size. For example, if your n is 100, so the number of ones, I mean the weight is just 10. 0.1 times 100 is 10. Okay? And there are only 10 ones in your solution. Other quantum algorithms, Bernstein, and on the other hand, Helm and May propose, and they reduce the complexities to 2 for 1 and 2 to 6. These are all based on the previous work, Graham Drew's work, or Baker, Coren, and Drew's work. They just add some quantum walks. I think they use quantum walks on the Johnson graphs in both proposals, and they reduce the complexity. This is a full table for with respect to alpha. 0.5 is actually corresponding to random knapsack. Okay, with Shamir algorithm, this is 0.5, 0.24 time and memory complexities. With this is better than this one, and this is by Baker, Drew, and Krohn, and this is obtained by quantum algorithm proposed by Helm and May. And if your alpha decreases, these complexities also decrease. Okay. How do we? Okay, this is all about generic algorithms. This way. As you see, all of the algorithms is exponential. Okay, 2 to the c times n. So all of them are exponential. Another way to solve the knapsack problems are lattice reduction. What is the lattice? Lattice is an integral combination of d linear independent vectors. I mean, you are given a basis. You construct a lattice by taking the integral combination of those vectors. The rank of lattice is d because the number of elements in your basis is d. You can represent your lattice by using matrix representation. You just write the bases as rows or columns in your matrix, and the volume of this lattice equals to determinant of B times B transpose, the determinant of the matrix B times B transpose. I think you also know the lattice problems, random lattice problems, closed vector problem, and the shortest vector problem. If you are given in CVP, in closed vector problem, if you are given a lattice and a target vector, which is not in the lattice, okay, you find the closest vector in lattice. In SVP problem, shortest vector problem, you're just given a lattice, and you're just trying to find the shortest vector in your lattice. Okay, how do we apply lattice reduction in knapsack? If you are given a knapsack elements A1 to AN, we can create a lattice so that there's coefficients y, x1, x2, xn. So that y equals to x1 times a1, x2 times a2, xn times an. I mean, the first component is written as an integral combination of the knapsack elements. So the natural basis for this knapsack is a1 can be written as 1 times a1 and 0 times everything. a2 can be written as 1 times a2 and 0 times everything. an can be written as 1 times an and 0 of everything. 0 times everything. So this is a natural basis for this lattice. And there is a good property about this lattice. You can easily compute the volume of this lattice with respect to your lattice, with respect to your knapsack elements. And note that if you are given a knapsack problem, this is your knapsack problem, right? Epsilon 1 times A1, epsilon 2 times A2, epsilon n times An equals to sigma. The corresponding vector or lattice point to this equation is sigma epsilon 1, epsilon 2, epsilon n. Because sigma is written as a combination of A1, A2, An with respect to coefficients epsilon 1, epsilon 2, epsilon n. These are coefficients as we define in the lattice. X are replaced by epsilon, y is replaced by sigma. So your vector sigma epsilon 1, epsilon 2, epsilon n lies in your lattice. So we have a lattice. Now we want to solve SVP or CVP lattice problems using this lattice. There are two approaches here. One approach by Lagrange Odilosco, another approach by Kostner. Okay, they say either. By the way, first choose two vectors, T1 and T2. T1 is just sigma and zeros. T2 is sigma and 1/2. Okay, these two vectors are not in the lattice part. Because can you write sigma is 0 times A1, 0 times A2, 0 times An? Can you write in that way? No, right? Because 0 times A1, A2, A3 is 0. So this is not in your lattice. Also, same for the T2. So these two vectors or 2 points doesn't belong to your lattice. Okay? So either you can solve closest vector problem using this lattice and the TK, okay, T1 or T2, or you can convert this CVP problem to SVP problem by extending the base of lattice by adding TK. How many elements are there in your bases? D, right? I'm sorry, N. There are N elements in your bases. And these two elements are not in the lattice. So you can just add this new vector in your bases, and you can have a new lattice. If you add this T1 in your lattice, okay, remember the basis for this lattice, A1, 1, 0, 0, A2, blah, blah, blah. In the end, you just add sigma 0, 0, 0, 0, 0, or sigma 1/2, 1/2, 1/2, okay? And you know that sigma epsilon 1, epsilon was in your lattice. So when you add this T1, the distance between your exact solution and your proposed vector, target vector, for T1, it is approximately square root of n over 2. For T2, it is square root of n over 4. And these two numbers are small. Okay? So if you perform a CVP oracle with those target vectors, you expect to get the solution, okay, which is actually 0, epsilon 1, epsilon 2, epsilon 3, epsilon 4, or epsilon I minus 1/2 in the second T2. And it gives you the solution. By the way, it's also possible to have, it's not guaranteed that the SVP oracle always gives you your solution. Why? I will just give a small example. For example, let's say one of your AI is 509 and another AI is 5180, okay? I mean, forget about the rest AIs. These two, just focus on these two AIs. Okay? Using the definition of the lattice, I can say 1 equals to negative 1 times 509 plus 1 times 5110, which corresponds to the vector 1, 0, 0, 0, 1, 0, 0, 0, 1, 0. This is 1 in the I position, this is I in the J position. What's the length of this vector? Just square root 3, right? This may be very, very small. I mean, let's say this is your n is, let's say 100, and your weight is 50, half of it. Okay? So the distance between your target vector and the exact solution is larger, very large, comparing to this lattice, this vector. So SVP Oracle will give you this vector, which is not a solution for your knapsack problem. This is not a solution for a knapsack problem. And it is a negative one. Okay? But this is a short vector in your lattice. So, to increase your success probability, you can scale the first column by k times a1, k times a2, k times an. But here, remember, I just replace AIs with k times AIs. Okay? AIs I replaced by k times AIs. And corresponding to my knapsack problem, I expect to reach that vector. Okay? Because if you multiply this equation with k times a1, k times a2, k times an, k times sigma, so your x1, x2, xn still epsilon 1, epsilon 2, epsilon n, but your y is k times sigma. So this is what you expect to have in this lattice. Okay? And if you multiply this first column with k, you will not have such a vector, because the gap between the AI and AJs becomes larger and larger. Here, the gap between AI and AJ is 1, correct? The difference between AI and AJ is 1. If you multiply with k, this gap becomes very large. I mean, k, at least k. Okay? So, you will decrease the chance or probability of having such vectors, and it will give you an exact solution with a high probability. I will just say density. Okay, we will, after talking about the lattice reductions, we have a density definition, D, defined as n over the logarithm of maximum of AIs. You are given the AI elements, you take the maximum of AIs, you compute the logarithm 2 of these AIs, and you divide this n with this number. According to Lagares and Odilowsko's lattice reduction approach, it works when this number is less than 6463. If this number is less than that number, Lagares-Odilowski approach will work. Koster's approach will work when this D is less than 0.9409. Okay, so Koster increased the probability of solving knapsack problem by using lattice reduction. But between this number and 1, the knapsack problems having density between these two numbers are considered as hard knapsack, which means we are not able to, we are not successfully able to apply lattice reduction. Even we apply lattice reduction, we will not get the exact solution. So forget about the lattice reduction. Go with generic algorithms. Okay. I mean, instead of applying lattice reduction on your knapsack problem, just go over with generic algorithms. The last part of my talk is our crypto system with Dr. Karagina, and we believe that this is a post-quantum secure algorithm. Let's start with the settings. We defined 3 finite fields. FP is the base field, FQ is the extension field. You pick an element in your extension field so that it is a quadratic non-residue, which means x squared, this is minus c, x squared minus c has no solution in this FQ. So using this root, let's say sigma is the root of x squared minus c, you extend your FQ to FQ squared. Let me draw this. You start with FP, base element, base field, prime field. You go to FQ, extension degree is m, because Q is big M. Then you pick an element here, but not quadratic residue. So x squared minus c has no roots in FQ. So if you take the root of this polynomial, you extend your FQ to FQ squared by adding this root into your extension, into your FQ. Okay? So this is the finite field setting we use in our crypto system. And this FQ square has a cyclotomic subgroup of order Q plus 1. The order of this Q plus 1. I'm sorry, subgroup of multiplicative, not FQ squared, the subgroup of FQ squared star, the multiplicative group of FQ squared. So Q squared minus 1 is the size of the FQ squared star, and this is our group. Is it okay to give like 5 or 10 minutes?
So maybe 5 more minutes? Okay.
Because we also start like 5 minutes late.
Yeah.
Okay. There is a good property of this group. There is a one-to-one correspondence, not isomorphism, one-to-one correspondence between that group and FQ. I mean, from this group, you can easily go to FQ and come back. Okay? So there's a one-to-one correspondence. But this group is actually in FQ squared. Okay? And you can represent each element of this group, non-identity element of this group, by an element of FQ. Alpha plus sigma, alpha minus sigma. Remember, this sigma is the root of x squared minus c, so sigma squared is actually c. And any element here is represented by alpha plus sigma, alpha minus sigma, where this alpha belongs to FQ. Okay? So you can represent the elements of G by using the FQ elements. This is our representation. When I say G sigma, it means G plus sigma, G minus over G minus sigma. The multiplication here, if you pick 2 elements, alpha sigma and B sigma, which is written in that way, when you multiply these 2 elements, you got another sigma another element written in the sigma representation as alpha A times B. C comes from this C over A plus B. So we can do the multiplication using the FQ elements, not FQ square elements. Okay? We can do the multiplication by using FK elements. And here, inverses are free. The inverse of this element is just the sigma of negative A. Okay, so inverses here are free. Okay, if you have an element here, like sigma, sigma is actually sub-sigma, okay, not prime sigma, written as multiplication of elements in FP. X sigma, this is in G. You want to represent this or decompose this element as product of GI sigmas. But this GIs comes from FP. Okay? So we want to decompose this G element, which is actually FQ square element, but we can represent by FQ, can be decomposable into some factors which can be represented by FP elements. So if I'm able to decompose this element in FP, this is an FQ square. But if I become able to decompose this element over FP with G1, G2, G3. This is the basic idea for our crypto system, and this decomposition becomes unique if the minimal polynomial of C equals to extension degree, which is n. This is very complicated. This may seem very complicated, but the F0 and F1 is just polynomials obtained by the symmetric polynomial AI. The symmetric polynomials are obtained using G1 to Gn. Okay? So when we get this this polynomials F0 and F1, we can find GIs. We can decompose actually using Weyl descent over FP. We just use linear algebra. We have n many unknowns and n linear equations. We just apply linear algebra. This is Weyl descent actually, and we can decompose into FP elements. So our crypto system, we have the FP, FQ, and FQ squared as I told before. The private key, some elements in FP, G1, G2, Gn. I will use this GIs as my basis, but this is secret. There are some other restrictions on this GI. Another non-zero element in FQ, an integer V, and another element in H. How I construct the public key? Now GI is in FP, right? In the basis element. If I multiply this element by U, I push this element to FQ, right? Because U is an element in FQ. Multiplication FQ element with an FP element becomes an FQ element. With sigma, I push this element to G. Now this element is in G. And I take the exponent, the V power of this element, G element in G, and then just multiply by H, which is in G. The HI, the last result I have as a public key, lies in G. Okay? I start with FP elements. I push this FP elements to FQ square elements, which is actually in G. Encryption is similar to other Knapsack crypto systems, and I also told this before actually. We just changed the additive knapsack to multiplicative knapsack. Instead of xi times hi, we just say hi to the xi, but we can also convert this to the additive knapsack by taking the discrete logarithms of both sides. And if you are given this ciphertext, you just remove this h. This is actually plays a role as a noise, as I told in the shorter best. This is like a noise. So first I remove this noise. There was a V as an exponent. So I take the power of 1 over V. This is actually 1 over V. So I come back to this multiplication. I remove the noise, I remove the exponent, and this is what I need to decompose. Here, I can decompose this multiplication, this element in that form using again well-descent method with a little difference. U is a FQ element. I want to have FP elements. So I also need to remove this U in my decomposition. Okay? So that's why I replace some terms. For example, instead of J to the J, I'm sorry, C to the J, I use U to the some power times C to the J, and then this U's can be removed. So what's our claims in our crypto system? All the classical knapsack solvers fail. All the quantum knapsack solvers fail. Lattice reductions fail. Algebraic methods, as what I propose, it fails. So in the end, it's a post-quantum secure. And these are parameters. I just want to give one parameter here. For example, take this to row. This is 0.09. This is the alpha, which means the number of ones in your solution. This is your P and M. P is your FP. M is the number of ones. N is the all knapsack size. The densities are very close to 1. So this is a hard knapsack, right? Forget about this too. The complexities using the generic algorithms, both in classical or quantum, these two numbers are like 2 to the 124 or 135. So it's like 128 bit security. Big easy doesn't work, as you see here. Very big numbers. Actually, the beta we get here is greater than n, so big easy doesn't work. And forget about this last part because this is just message space, ciphertext space, blah blah. So, I mean, we have parameters for 128-bit security, 192-bit security here, and 256-bit security here. As you see, P is not big enough. Just M is big. I mean, P to the M becomes very large. And it affects to the public key size. Because we should represent the public keys as a FQ square element, and Q squared is a P to the 2M, 2M times log P size. So I mean, it's like kilobytes or megabytes maybe. So is knapsack problem post-quantum secure? We still don't know.
Okay, so that's a good question. So I have to stop here. Let's thank Emrah on top. Are there any quick questions? We're already out of time. If no quick question, I mean, we can further discuss it after the talk.
Okay. Thank you very much.
Let's thank